Okay, so let's start. So today we'll solve two questions from real analysis. One is question number 53 from Gate 2020 and another is question number 40 from Gate 2021. Okay, let's start. Okay, so today we'll solve Gate 2020 question. This is a question from real analysis. It's a question number 53. So it's saying that the coefficient of x minus 1 to the power 5 in the Taylor expansion about x equals to 1 of the function fx, which is given by this from x belongs to x from 0 to 2, is you have to find the basically, so the x minus 1 to the power 5 coefficients of the in the Taylor expansion of this term x minus 1 to the power 5. Okay, so basically you have to write it in of the form fx in terms of Taylor expansion at about the point x equals to 1. Okay, so this is the NPTEL reference. This you can check. Okay, let's start. So what is fx first? It's 1 to x log e base t by t minus 1 dt for 0 less than x less than 2. So we have to find the Taylor expansion of f. So first, so that for that, to finding the coefficient of x minus 1 to the power 5, that you can also do that differentiating a 5 times, so that you will get the, because what is the coefficient for the Taylor expansion of x minus 1 to the power 5? It's derivative of f 5 times at the point 1 by 5 factorial. So that you can also compute. But if you compute the derivative 5 times, it will be cumbersome. It's not easy. So we'll use that log. We can expand the in terms of power series. We know expansion of log that we can use. So let's first check. So what we will do? So first, just write down this one. Log, we write it of the form 1 plus t minus 1. So that because in the numerator t minus 1 is there, so that's why I'm writing in this form t minus 1 dt. So what is the expansion for log? So it is 1 by t minus 1. So this is the series k equals to 0 to infinity minus 1 to the power k x by x to the power k by factorial k. So 0, it's positive power. For 1, it should be minus. So t minus 1 to the power k. So k 0, k equals to 1. So what is the Taylor expansion? K equals to 0 to infinity minus 1 to the power k. For x, coefficient of x should be positive, right? And coefficients of x square should be negative. So coefficients of x means t minus 1, this coefficient, so k plus 1 by k plus 1, right? On k equals to 0 you get t minus 1, that should be positive. Yeah, so dt. So 1 to x, now divided by t minus 1, what you will get, summation k equals to 0 to infinity minus 1 to the power k. So if you divide it by, what you will get, t minus 1 to the power k by k plus 1 dt. Okay, so we'll get this. Now suppose we can interchange this summation and integral. So when we can interchange the summation and integral, if this series is uniformly convergent, then the summation and integration we can interchange. So first assume that we can interchange the summation and integral. So assume this one, we'll prove it later. So assume that this you can do it. So now you can integrate it. So now what will happen? So let me write it in red. Assume this one. We'll prove it below. So now if you integrate this, what you will get, k equals to 0 to infinity minus 1 to the power k. So it's t minus 1 to the power k plus 1 by k plus 1 whole square, right? So we'll get this. So this is the, so this if you, oh sorry, now evaluated from 1 to x. So if you evaluate this, k equals to 0 to infinity, at the point x you will get minus 1 to the power k, x minus 1 to the power k plus 1 by k plus 1 square, and at 1 it will get 0. So fx will get this. So fx is summation k equals to 0 to infinity minus 1 to the power k by k plus 1 square, x minus 1 to the power k plus 1. Right, so we'll get of this form. So note that this is exactly the Taylor expansion of f about the point 1. So for k equals to 0, what we will get? K equals to 0, it's x minus 1. K equals to 1, we will get minus 1 by 4 x minus 1 square plus dot 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 k equals to 4, you will get 1 by 25 x minus 1 to the power 5 minus dot dot dot. So the coefficients of x, so this is the note, this is the Taylor series expansion of f about the point 1. Right. So the because so the coefficients of x minus 1 to the power 5 is 1 by 25. So we'll get the coefficient of x minus 1 to the power 5 is 1 by 25. Now we have to prove that why you can interchange this summation and integral, right? So you have to justify this one, why we can interchange the summation and integral, right? Okay. Now we have to check why we can interchange the integral and summation. What we have done, 1 to x summation k equals to 0 to infinity minus 1 to the power k t minus 1 to the power k by k plus 1 dt for 0 less than x less than 2. Why this is same as k equals to 0 to infinity 1 to x minus 1 to the power k t minus 1 to the power k by k plus 1 dt. Right, this we have to check. So note that there is one result that means this is basically when you can interchange the integral and summation. So if this series is uniformly convergent, then we can interchange the summation and integral. So this is one result. So let fn be from an interval. So let's say some ab to r be integrable on I if summation fn is uniformly convergent on I, then so basically then you can do this summation fn integral over I fn x dx is same as summation or a to b over n fn x dx. So it's saying that if the series is uniformly convergent, then we can interchange the integral and summation. So for that, here we have to check that this series is uniformly convergent. This series. Here we have to check summation k equals to 0 to infinity minus 1 to the power k x minus 1 to the power k plus 1 by k plus 1 is uniformly convergent. Okay. So note where is x? Note uniformly convergent where? For x in, so uniformly convergent on some compact set we need, right? So where, so note x is in, so 0 less than x less than 2, and in integral of t where t is from 1 to x. So where t will lie basically 1, this is less than t, which is less than, strictly less than 2, and in the series we have so this series for series of t, and t is, so t minus 1, where t minus 1 will lie, so which imply as t is less than, so 1 less than t, so we can write this should be less than 2 minus delta for some delta positive. So t lies in this, which implies 0 less than t minus 1 is less than 1 minus delta. So uniformly convergent for t minus 1 should belongs to in this compact set. There we have to check the uniformly convergent. Right. Now to checking the uniformly convergent, here will this series will use the Weierstrass M test. Let me recall. So let Mn be sequence of positive real number and suppose and fn x is less than mn for all n belongs to natural number and x belongs to in some domain where we will dealing with. And if the series summation mn is convergent, means finite, then summation fnx is uniformly convergent. Right. So it is saying that let fn be a series of function if each fn is dominated by mn, where this mn is convergent, then this series is uniformly convergent. Right. So okay, we will use this Weierstrass test to prove that this series is uniformly convergent. So for that we need the sequence of positive real numbers. So here we will take the mod. So let's check. So here the series is so first note, what is this minus 1 to the power k t minus 1 to the power k plus 1 by k plus 1. So what you can write, so this is less than, oh, so where t is belongs, t minus 1 is in 1 minus delta. So t minus 1 is less than, so t minus 1 is less than 1 minus delta. So this we can write 1 minus delta to the power k plus 1 by k plus 1. And this k plus 1 is bigger than 1. So this you can write 1 minus delta to the power k plus 1 or delta bigger than 0. So note that when delta is obviously less than 1, we can, for this is a small delta. So take here mk to be this, for delta positive and less than 1. So note this series summation k equals to 0 to infinity 1 minus delta to the power k plus 1 is finite, as it is a geometric series. With this x to the power k plus 1, where x is less than 1. So this series, so basically summation mk, this is finite. So by Weierstrass test, this series summation k equals to 0 to infinity minus 1 to the power k t minus 1 to the power k plus 1 by k plus 1 is uniformly convergent. So therefore, by this result, we can interchange the limit and integral, right? Okay. So therefore,
Are you? Is it booked? Okay. Sorry.
as below, we have shown that here we can interchange the integral and summation. Okay. Okay, so what we have, so what is the question that we have to find the coefficients of x minus 1 to the power 5, that we have found out 1 by 25. Okay, so the answer is 1 by 25. So correct up to 2 decimal places. Okay, so this is 1 by 25. So which is 0.24. Right. Zero point 0.04. Okay. Okay, so any doubt or any question?
So good evening, sir.
Yeah.
Good evening, sir. Yes, sir, I understand last.
Okay.
Yes, sir.
Okay.
Sir, I want request, sir.
Yeah.
Last month slide, can you share me if possible?
Last one means which one?
Last 1 month slides, sir. I missed last 1 month class.
Oh, slides. Okay. Yeah, yeah.
Possible.
So you can access the recordings, right?
But the recordings not working in my mobile, sir.
Okay, so I will upload there also the slides.
Okay, sir. Okay, sir.
Yeah, in my
But
folder. In my folder you can find in recording folder.
recording folder. Okay, sir. Recording folder video only there, sir.
Yeah, yeah, there I will upload.
Okay, sir. Okay, sir. I will get.
Yeah, yeah.
Thank you, sir. Today's class over?
No, no, no. There is one more question. I will solve.
Okay, sir. I'm waiting.
Okay, so let's move to the next one. Okay, so today we'll solve Gate 2021 question. This is a question from real analysis. or calculus. It's a question number 40. So it is saying that let the equation xy minus z log y plus e to the power xz equals to 1 can be solved in a neighborhood of the point 0, 1, 1 as y equals to f of x comma z for some continuously differentiable function f. Then you have to find the gradient of f at the point 0, 1. And you have to check which one is correct. Okay. So this is the NPTEL reference. This you can also check. Okay. So let's try to solve. So this is saying that this implicit equation is saying that can be solved in a neighborhood of this point as a function of y as a function of x comma z. So basically implicit function theorem gives us this kind of, that when you can solve something in terms of the other variable. Okay, so let me first recall what implicit function theorem. Let me first write down what it is. Xy minus the equation is given xy minus z log y plus e to the power xz equals to 1. This can be solved in a neighborhood. Can be solved in a neighborhood of 0, 1, 1 as y equals to f of xz. Right. So basically implicit function theorem gives when you can solve one variable in terms of others. So let me write the implicit function theorem. So implicit function theorem so I am writing it in general. Let f from some open set omega to Rm be a C1 function, means continuously differentiable function. On the open set omega, which is omega n cross omega m of, this is the open set in Rn plus m, such that f of ab comma 0 for some point ab in omega. So if determinant of this del f by del y, so del f by del y, now it's with respect to y, it's a function from Rm to Rm. If this determinant is non-zero, then there exists a neighborhood UA cross UB of AB, of that point AB in omega, and a C1 function f from UA to Rm such that f of x comma fx is 0 on the neighborhood UA, and fa is b, right? So this is the implicit function theorem. So it is saying that if this is a, suppose a C1 function is given on an open set omega n cross omega, and at some point f of ab it's 0, and saying that let del f by del b, so f with respect to when you differentiate y, so we are viewing at a function from omega m to rm, means the linear transform, this is a linear transformation, it's a m cross m matrix, so determinant is well defined. If it is non-zero, then there exists a neighborhood ua cross ub in omega and a c1 function such that f of x comma fx is 0. Means in that neighborhood where this derivative is non-zero, so here the del f by del y is non-zero, so second coordinate y you can write as a function of x, right? And fa is fb. So where which derivative is non-zero, so that variable you can write in terms of the other, right? So here we have this, here let define f of x y z to be xy minus z log y plus e to the power xz minus 1. So here we have solved, we can this can be solved at the point 0 1 1 as y as a function of xz. So for that we need to check that del f by del y should be non-zero. So let's check. So as this can be solved as y equals to f of xz. So let's check del f by del y. What is del f by del y? Del f by del y means partial derivative with respect to y, so it is x minus z by y, so this only. Then del f, so del f by del y at the point 0 1 1, it will be 0 minus 1 by 1, so it is minus 1, so it is non-zero, right? So y can be solved as a function of xz, so it's fine. And what, right, now we have to find the gradient of y. So to find gradient of this small f, right? So this is basically y, so gradient of f at some xz point means this will be basically del f by del x small f comma del f by del z, and as y is f is basically y, so basically dy by del y by del x, this is del y by del z, right? So that we have to find. So this is grad f. Now we have, okay, so let's find what this is. And what we have also, we have f of 0 1 xz is 1, right? So what is the equation we have? This is the equation. This is the equation we have, xy minus z log y plus e to the power xz equals to 1. So this we can differentiate with respect to x. So differentiating with respect to x, we get, so differentiating with respect to x, what you will get, y minus, so y is a function of x. So first when you differentiate with respect in x, you will get first derivative of x is 1, so y plus x del y by del x, as y is a function of x and z, minus, so z is independent variable now, and if you differentiate this, you will get, so this will get z by y del y by del x, and xz, if you differentiate with respect to x, so you will get plus z e to the power xz equals to 0, right? Or so x minus z by y del y by del x is minus y minus z e to the power xz. Or so what will be del y by del x? So del y by del x will be minus y plus z e to the power xz by x minus z by y. So if you simplify, what you will get, y square plus yz e to the power xz by z minus xy. So del y del x we got. Now we have to find del y del z. So now we will again differentiate this with respect to z. Now differentiating with respect to z, we get, so if you differentiate with respect to z first, what you will get, first y is a function of z, so x, so let me write the first equation here, as this is xy minus z log y plus e to the power xz equals to 1. So differentiating with respect to z, we'll get x del y del z minus log y minus z by y del y del z plus x e to the power xz equals to 0. Now as early, collect the term for del y del z. So log y minus x to the power xz or del y del z log y minus x to the power xz by x minus z by y. So y into log y minus x to the power xz by xy minus z. So therefore what is the gradient? Therefore gradient of f is, so del y by del x, this is y square plus yz, y square plus yz e to the power xz by z minus xy, and this one is y into log y minus x to the power xz by xy minus z. Now we have to find gradient at the point 0 comma 1, right? So gradient of f at 0 comma 1, and f at 0 comma 1 is basically 1. So put x equals to 0, basically this. Means x equals to 0, y equals to 1, z equals to 1. So if you put it here, what you will get? y1, so it's 1 plus yz1, so it's 1 by z1, comma y is 1, log y is 0 minus, so it's 0. So it's 2 comma 0. So gradient at the point 0 comma 1 is 2 comma 0. Okay, so this is the answer. So therefore which answer is correct? So 2 comma 0. So therefore option number A is the correct one. Okay. Okay, any question?
No, sir. No, sir. Very nice, sir.
Yeah.
I understand clearly.
Yeah, okay, then fine. So I think in the next week there will be 2 hour session.
Okay, sir.
Hmm.
Okay, sir. Kindly share notes, sir.
Yeah, I will share the
Recording.
notes. Yeah.
Okay.
Hmm.
I will find.
Yeah. Thank you.
Thank you so much, sir.
Hmm.
So is this class over, sir?
Yeah. If you have any doubt, you can ask. Otherwise, today's class is over.
Okay, sir. Sir. Okay, so let's stop for today.